Good morning, everyone, and welcome to our presentation. Today, we're going to talk about securing your cluster network using Calico and OSH Infra. Before starting, allow us to introduce ourselves. My name is Nishant Kumar, and I work for Ericsson as a software engineer. And as part of Ericsson, I work for AT&T's Network Cloud, and I'm one of the developers in the Airship project. And today, I have with me
I'm Meg Heisler. I work at AT&T. I'm a software engineer in AT&T's Network Cloud, and I work largely with Openstack-Helm.
Okay, so setting up the agenda, today we're going to talk about network policies that are provided by Kubernetes to secure our cluster. I will be starting off with the policy introduction and then talking about Kubernetes native network policy as well as the Calico's network policy. We'll be looking a little bit into the network policy terminologies provided by Calico as well. Then I'll be showing a small demo as to how these network policies work. Then Meg is going to talk about the Helm charts and how OSH Infra and Calico charts would ease your process of applying these policies. And then she'll be also showing a small demo. So what happens when you try to deploy a set of pods from a networking perspective, especially in a Kubernetes as a multi-tenant platform or a shared PaaS? So by default, every pod in the cluster can talk to every other pod. Kubernetes does not restrict any incoming traffic. It has no firewall rules for any inter-pod communication, thus making your environment vulnerable to security threats. Now, as Kubernetes is adopted by organizations' IT environment, security controls will need to be applied to manage fine-grained access controls to application workloads. In this case, we're talking about pods, and also managing these restrictions dynamically on a running workload to allow or deny a traffic. So in order to provide a simple yet native interface for management, Kubernetes came up with the network policy object. And what this means is that if you define a network policy rule where you do not want two pods to be talking to each other, no matter what happens, if one pod tries to connect to another pod, those policies won't allow anyone that interaction to go through. So that's the power of network policy within Kubernetes. So again, network policy, it's a set of network traffic rules applied to a given group of pods. Now what these rules looks like is what we're going to see in the further slides. Talking about the network traffic rules, we have two different types of traffic, one being the ingress and one being the egress traffic. So ingress is the traffic which comes into your pod, and egress is the traffic that goes out of the pod. A network plugin from a network policy perspective plays a very crucial role. So although Kubernetes does allow you to define a network policy in your pod templates and you could create a network policy, but unless you have a CNI plugin which actually implements those network policy, your policies are not going to take any effect. So you need a good choice of network policy or a CNI plugin that implements these network policies within Kubernetes. So some of the examples are Calico, Romana, and Weave. For this presentation, we are going to focus more on Calico and look into some of the features that Calico network policy provides into securing your cluster. So first, talking about the Kubernetes cluster, if you're trying to use the native Kubernetes API or the native Kubernetes network policy, this is the API version that you would be using. It has supports for traffic rules based on protocol, port, source, and destination IP addresses. So you could use multiple permutation and combinations. And depending on your requirement, you could define your policies within a policy template file. And then you could also filter traffic based on pod and namespace labels. So if you have a requirement where you would like to allow a traffic between different namespaces and between different pods, then Kubernetes has these features, has these filters, which you could define in your network policy definition, and you could easily apply these policies. So talking about Calico, Calico is a superset of Kubernetes policy. So although it supports all the default network native Kubernetes policies, it also has some additional features that could be pretty useful for your cluster. So if you're trying to use Calico's network policy, you have to use this particular API version. And it has support for allowing or blocking traffic for pods across different namespaces. So Calico has a network policy object called global network policy. So once you apply that, it will be applied across all the namespaces, across all the endpoints that are exposed within your cluster. And then you can also block inbound ingress traffic to Kubernetes load balancer or node port. So by default, Kubernetes node port, load balancers, and ingress services make your app available to public and private cluster networks interfaces. But when you're using Calico, its default allow node port DNAT policy permits incoming traffic from any source IP addresses. And then Kubernetes uses its regular DNAT to forward your service request to the correct pods. Now, however, for security reasons, you might need to allow traffic to the networking services from a certain source IP addresses only. And in this case, you can make use of the Calico's pre-DNAT policies, which is used to whitelist or blacklist traffic from a certain IP addresses. Now, these pre-DNAT policies prevent specific traffic from reaching our apps because they are applied before Kubernetes applies its regular DNAT. As a best practice measure, it's always suggested that you have a whitelisting policy which provides the most secure configuration, and you could block traffic except from known permitted source IP addresses only. Also, it has options to allow or block traffic from different networking interfaces. So Calico sees a couple of different interfaces called the host endpoint and workload endpoint, which we'll be talking about later. And it has policies and features to block those traffic as well. So this is a particular example as to how a network policy looks like in a Kubernetes world. So looking into it a bit more closely, as any API object definition, you have the API version, kind, and metadata. So the important part here to look is the spec part. So network policy spec has all the information needed to define a particular network policy in the given namespace. And then you have a pod selector. So each network policy includes a pod selector, which selects the grouping of pods to which this policy applies. So this example selects pod with the role equal to DB. If you don't have any pod selector, then it would select all the pods in that given namespace. You also have different policy types. As I said earlier, you have ingress and egress types. So you can define either of them or both of them. And then you have the rules. So in this example, you have an ingress rule. So each rule allows traffic which matches both the from and the port section. So this example policy contains a single rule which matches traffic on a single port from one of these sources. The first specified via an IP block, the second via the namespace selector, and the third via the pod selector. And then you also have the egress rules. So each network policy, again, contains a list of whitelist egress rules. Each rule allows traffic which matches both the to and the ports section. So the example policy contains a single rule which matches on a single port to any destination on this given IP address range. So now taking a look into the Calico's network policy object. Again, it represents an ordered set of rules which are applied to a collection of endpoints that match a label selector. So it's pretty similar to what Kubernetes sees a network policy object as. And network policy within Calico is a namespaced resource. So if you apply a network policy object, it will be only specified or it will be only confined to one namespace. And then this is used to define network connectivity rules between Calico endpoints and host endpoints. This is an example of how a Calico network policy object looks like. So we have, if you would like to use Calico network policy object, this is the API version that you would be using, which is projectcalico.org/v3. Again, it has the kind and a metadata. So within this spec, it looks pretty much similar to what a Kubernetes policy looks like. So in this, we have a simple rule that allows incoming traffic on port 6379 for the endpoints that carry the label app equal to database. And when the source is from the endpoint which carry the labels role equal to app front end, then that traffic will be allowed. So this allows a declarative way of specifying rules between a group of endpoints matched based on the label selector. So this is a kind of a table, a default table. So if in a network policy definition, you do not have this types section. So this is what the default rule looks like. So if you do not have any type section, by default, Calico assumes that it is an ingress policy. So if you just have an ingress rule and not an egress rule, so by default, Calico assumes it's an ingress rule. And if you just have an egress type, then Calico will assume it's an egress rule. And then if you have both, then Calico will apply those policy to both the ingress and the egress traffic. And again, this is various options and parameters that can be supported via Calico's rule section. So if you look closely here, the portion which starts from action and goes up to 6379, this is a kind of one rule. Now you have different options here supported, like action, protocol, ICMP, source, and destination. So you could use different features, different parameters depending on your requirement, and then you could apply policies within your cluster. So this is an example for a global network policy object. So as I said earlier, that Calico supports applying network policy across all the namespaces. So you just have to use the kind as global network policy, and everything else looks the same. So if you look from the previous example, it's pretty much the same. The rule looks the same, but the application would be different in terms that this particular policy would be applied across all the namespace and across all the endpoints that Calico is aware of. So again, this is not a namespace resource, and this above policy will define that incoming traffic is allowed on port 6379 for the endpoints that carry the label app database, and when the source is from the endpoints which carry the labels app equal to front end. Calico also has a profile resource object. So profile resource object represents a set of rules which are applied to the individual endpoints to which this profile has been assigned. So Calico has some set of endpoints like workload endpoint and host endpoint. So we can apply this set of profiles on those endpoints. Each Calico endpoint or host endpoint can be assigned 0 or more profiles. So the following sample profile allows all traffic from endpoints that have the label set to profile 1, except that all traffic from this particular IP range will be denied. So as I was talking about different endpoints that Calico sees, one of them is a workload endpoint, and this is how you define a workload endpoint within Calico. This is what the definition looks like. Your kind becomes a workload endpoint. You have the metadata and you have the labels. And again, in the spec section, you could define different options. So basically, workload endpoint represents an interface connecting a Calico networked container or VM to its host. So, and a workload endpoint is a namespace resource. So within the spec, you could provide the node name, you could provide the orchestrator, which is the Kubernetes itself, you could have the container ID, you could have endpoints, and you could have a list of profiles that we saw earlier could be applied to this particular endpoint, and you could also give a list of named ports that this workload exposes. So another type of endpoint which Calico sees is the host endpoint. So Calico provides features to secure our host interfaces as well. So a host endpoint resource represents one or more real or virtual interfaces attached to a host that is running Calico. And this is a example definition. You have the interface name as ETH0. You could have the interface name as star as well, and it will represent all of host's real or virtual interfaces. Now each host endpoint may include a set of labels and a list of profiles that Calico will use to apply policy to these interfaces. If no profiles or labels are specified, Calico will not apply any policies. And Calico also has supports for application layer policies. So application layer policies is enforced against application layer which has attributes for HTTP methods. So you have an example, and you can provide endpoints in this endpoints project /Calico, and you could apply those policy into HTTP endpoints as well. So these HTTP match, there's an HTTP match attributes of an HTTP request, and the presence of an HTTP match clause on rule will cause that rule to only match HTTP traffic. Support for application layer is not enabled by default in Calico installs, since it requires extra CPU and memory resources to operate. So you'll have to enable it additionally on top of this. So Calico has some features for fail-safe rules as well. So when a host endpoint is added, if there is no security policies for that endpoint, then Calico by default is going to deny all the traffic to or from that endpoint. So that could result in removing all connectivity from your host. And that is not a desirable situation. So you would always want some kind of connectivity towards your host in case you would want to do some kind of debugging. And therefore, you have Calico fail-safe rules. They are overly broad in allowing inbound SSH on any interface and allowing traffic out to HCD's ports on any interface. Now, depending on your network, they may not cover all the ports that are required. For example, your network may have maybe allowing ICMP or DHCP. So therefore, it is recommended to create a fail-safe rule or policy which is tailored more towards your environment. So this example fail-safe rule shows one example of how you might do that. The command uses the Calico CTL create to create this fail-safe rule policy, and it applies to all known endpoints since this is a global network policy. It allows inbound SSH access from my management subnet. It allows outbound connectivity to HCD on a particular IP address. If you have multiple HCD servers, you should duplicate the rule for HCD destinations. Then it allows for inbound ICMP, and it allows for outbound UDP on port 67 for DHCP. So this is an example fail-safe rule, and it's always recommended that you have one for your environment as well. So how does Calico enforce these policies? So basically, these policy rules are defined in the above resources, and they're translated into IP tables and IP set rules. The Felix agent that Calico runs as a daemon set or Kubernetes reads this network policy and then translates them into an IP table rules and IP set rules, and that's how these policies are applied. So now I'll be showing you a quick demo of how network policy works. So first, I'll be creating a pod, and then I'll be showing that I'll limit the connectivity towards that pod, and I'll be blocking and allowing through a demo. So first, we'll look into the environment. So we have the normal Kubernetes components running. You have Calico running. You don't have any pods as of now, and you do not have any network policies applied in this environment so far. So we'll go ahead and we'll create a pod. And this pod will have label front end and API, and it will be exposed as a service. So once we run this, a pod is created, a deployment is created, and a service is created, as you can see it here. Then we'll be creating a network policy. This is the example policy that we're talking about. You have the metadata, and then you have the pod selector. So this policy will be only applied to pods with the labels having front end and API. And then we have one rule which is, sorry. So we have one rule here, and this will match with the app having front end. So we'll be creating this network policy using kubectl commands. And now you can see that a network policy has been created in your cluster. Now we'll go ahead and create another pod, and this time the pod will have no labels attached to it. So when this pod tries to connect to the service, that request should not go through. So this is an example of creating a pod without labels. We'll grab the service IP address for the previous deployment and service which we had created. So here we have grabbed the service address, and we'll try to connect to it, and we'll see that the connection will not go through because of the network policy that we have applied, and this pod does not contain the labels that are required to connect to that service. So you can see that the connection has timed out, and the policy works as expected. Now we'll create another pod which will have the required labels. So this time this pod has the labels front end and the role API. So as per the network policy rule, this connection should go through because this pod has the labels as expected by the network policies. So we'll try to create this pod, and then we'll exec into it. Again, we'll grab the service address for the deployment and service we created earlier. And again, this time we'll try to connect with the service, and this connection should go through since this pod had the required labels. And here you can see that the connection has gone through, and thus network policy is working as expected. It is blocking traffic, and it is allowing traffic as per the defined network policy definitions. So here now I would like to pass this presentation to Meg, who will be talking about Helm.
Thanks. Thank you. I'll be talking about how OpenStack-Helm handles these network policies, but to go over that, first I'm going to talk a little bit about Helm and get you up to speed. So Helm is often described as the apt-get or apt-update of Kubernetes. It uses a package format called charts, and a chart is a collection of files that describe a related set of Kubernetes resources. A single chart can be used to deploy anything simple like a memory cache pod or something complex, such as a full web stack with HTTP servers, databases, caches, so on. So using Helm, it becomes much easier to deploy, upgrade, and delete, as well as version deployments, package deployments, and create a release as a set of charts. For example, if you run helm install command, it will talk to the tiller service, which is installed as in cluster component. Tiller receives the request for installation and talks to Kubernetes API server to spawn the resources as requested. So Helm is going to handle pretty much all of that. So this is sort of how Helm is set up. A chart is organized as a collection of files inside of a directory. That directory name is the name of the chart. Thus, the chart describing Keystone is going to be stored in the Keystone directory. Charts are created as files laid out in a particular directory tree. Then they can be packaged into version archives and deployed. So sort of going through this, the chart YAML is information about the chart stored in a specific file. The chart YAML is required. Every chart must have this file. The requirements is just all of the dependencies for the chart, and the chart directory overall is a directory containing any charts upon which this chart depends. So if we have a chart that needs to talk to another chart, that's going to be stored there. The templates is a directory of templates that when combined with values will generate the Kubernetes manifest files. And then the values YAML is our configuration file. So it's highly likely that your configuration file will rely on many different things in that template file. So here we have a values file. As you can see, we're just setting up a replica, one API. So and this is our template file. We can see that in the replicas, this is the location where we're going to specify how many we need. So it makes it as easy as changing it into the values file and never having to go and define that all over the place. So this is OpenStack-Helm. It's an official OpenStack project that utilizes Kubernetes, Helm, and OpenStack all together to support the OpenStack services. Openstack-Helm provides a collection of generic Helm charts for the OpenStack services and their dependencies. Using these OpenStack charts, the OpenStack services, With OpenStack-Helm, a new user can easily deploy an entire OpenStack environment just using these charts. So you can go ahead and run multiple things, and you will have Keystone, Nova, Glance, anything that you need, you can find in OpenStack-Helm. Then OpenStack-Helm Infra is the collection of Helm charts for third-party services used by OpenStack-Helm. So if things like Keystone use RabbitMQ, you can find a chart for RabbitMQ in OpenStack-Helm Infra. Infra also includes charts for all of your logging, monitoring, and alerting needs, so you can better monitor and track the health of your overall environment. So this is where Helm and Calico sort of meet. Calico charts can be found in the OpenStack-Helm Infra repo, and here are some of the important files that can be found under the templates directory. Calico uses the following components to achieve this. A Calico node container that runs 2 daemon processes. So Felix, which is the component at the heart of networking for Calico. It runs on every node in the cluster, and it's responsible for the interface and the route management, state reporting, and the policy enforcement. So Felix is really the Calico part that runs everything else. Without it, the whole thing doesn't work. And then the bird BGP daemon, which is optional. It distributes routing information written by Felix to other bird agents on the cluster node. The bird agent is installed with the Calico daemon set pod. This ensures that traffic is routed across all nodes. This means that every bird, Calico by default creates a full mesh topology, so every bird agent needs to be connected to every other bird agent. The etcd folder, Calico uses a distributed data store called etcd that stores the Calico resources, configurations, and network policy rules. The Felix daemon set communicates with this data store for publishing routes and route information, and also interface information for every node, among other information. For higher availability, a multi-node etcd cluster should be set up for larger deployments. In this setup, etcd ensures that Calico configurations are replicated across the entire cluster, enabling them to always be in the last known good state. And then finally, we have the Calico controller. This is the policy controller that watches over all network policies and programs that Calico sort of controls. Removal or changes to the network policies are reflected by the controller loop, which ensures that the policy changes are applied to workload in real time. So we're going to sort of look at an example chart. This is just a Helm chart. This is the values.yaml, where we're defining sort of our policy in there. So we're saying we want to allow any egress or egress traffic. We only want to allow traffic from pods with the role titled front end, and we want to allow all egress traffic. Helm doesn't itself do that. So we have a Calico job set up to interpret that file. Using this, anybody running OpenStack-Helm never has to touch Calico itself. They simply mess with the values that they would want in the value YAML, and otherwise don't have to worry about setting up any Calico configurations. So we'll run through a quick demo. For this, we're kind of going to go through just 3 things. We're going to look at Grafana, Prometheus, and MariaDB. These 3 things all have to talk to each other. So they need a network policy between them if we're going to try to make the cluster secure. So we're going to start off with a deployment. These are the things we're running. As you can see, Ingress and LDAP have already been installed, and so has Kubernetes. First, we're going to go ahead and look at this general network policy. This chart will basically lock down the entire cluster, so it stops all traffic between all pods, therefore isolating them. Without setting up a network policy individually for each deployment, they won't be able to talk to each other. So any dependencies are no longer able to communicate with the things that they're dependent on. We have to set that up later. So we'll go ahead and run this, therefore locking down everything that we're going to deploy. So next I'm going to go ahead and deploy MariahDB. I'll show you in a second what the chart looks like. But as you can see, MariahDB comes up just fine, even with this lockdown chart being in place. So everything starts running, and we're going to look at what was just run. So we ran a script to install both the basic MariahDB chart, but here we have these networking policy overrides. In these overrides, we are specifying that MariahDB now does have a network policy. Not only does it have a network policy, it has an ingress policy on 2 different types of pods. This Prometheus MySQL exporter only talks to Prometheus. It only receives traffic from there. So that's the only thing that it needs an ingress level for. MariahDB, however, receives traffic from both Grafana, MariahDB itself, and Prometheus MySQL exporter. You can see that the ports have also been defined what traffic it can receive from. So without these, MariahDB wouldn't be able to receive traffic from anything. But because we've defined these, when we go to deploy Prometheus and Grafana and everything else, we should be in good shape. Oh, there we go. Okay, so everything came up, it's running, and now we are going to deploy Prometheus. So that started. Without that ingress policy that we put into place for MariahDB earlier, that would not have worked. So we can go ahead and look at the Prometheus deployment that we just ran. This is the override for the network policy that we put into place for Prometheus. It receives traffic from a lot more than just MariahDB. So it has to receive traffic from Prometheus itself, because if you don't set up the ingress traffic to the pod itself, it can't even communicate with itself. So now that was run, the last one is Grafana. Grafana is fairly simple, but it does deploy the most pods. And it's heavily reliant on MariahDB and Prometheus. So that is running. And we'll go ahead and look at what we just implemented. All right, so this is the Grafana network policy. Again, very simple. Grafana only needs to talk to itself. And then the ports that it receives traffic from are just the default port 80 and the port that Grafana relies on, 3000. So now that we have these 3 things into place, we should be able to have them talk to one another. Okay, so that's all finished. Grafana is up and running. So this what we're going to look at next is a script. Is a script that can be used. It resides in Openstack-Helm Infra, and it sort of can be used as a tool to verify that your pods are now able to talk to each other or that they're not. So we're going to test the connection from one of the applications to another one using just a wget, and we will go ahead and find the pod and the pod ID from information that we provide in the script. So we'll try to enter the pod. If we receive our expected return, then we know whether we were successful or not. So we're going to try to connect from MariaDB to Prometheus, which should not work, and then from Grafana to MariaDB, which should work. We'll run this script. So first, again, from MariaDB to Prometheus, we don't expect this to work. All right, so what happened was, again, we tried to connect from MariaDB to Prometheus using everything we gave it, which was its namespace and a few other specifiers. And the connection timed out exactly as we expected. This wouldn't have happened without that lockdown chart that we had earlier. Now, thanks to the ingress rules we put into place and our values, that lockdown chart was able to maintain. For our next one, we were expecting Grafana to be able to reach MariaDB, and this worked. So it operated exactly as expected. Those rules were implemented, and now there's an ingress layer between MariaDB and Grafana.
So I think that's it from our presentation. So I think one takeaway from this would be that in your Kubernetes cluster, please define network policies. Please define Calico safe rule policies, and ensure that your Kubernetes cluster is secure and safe. And that's it. Thank you.